Hi everybody, internet world, it's MoNaCo here.
And milks?
We are starting our fifth unit, moles and stoichiometry.
Yeah, the fifth and maybe our favorite unit.
Yeah, as a chemist, this is definitely my favorite unit because it involves actual chemical reactions, measuring quantities in the lab,
A little bit of math.
predicting outcomes and consumed products and reactants, all that kind of stuff. And
Yeah, there's a lot of real world, real laboratory type stuff that we can get into.
both you and I did this at Kodak, and if you
yeah.
haven't watched our first intro video,
Hope you did.
yeah, it's actually Milks and I in the lab doing some moles and stoichiometry to make a chemical compound that is very relevant to Rochester's history, we'll say.
Yeah.
And the second video is just us making sure that we actually got what we were supposed to.
Which is a cool thing, that predicting piece is
Yeah.
something we can do with this unit. So,
But this unit, unlike other units, we're front-loading our vocabulary in with the video. We've never done that.
And I think we're going to do it, if it works out well, for the rest of the year.
Yeah, it's a simple video. You get new definitions, and remember, you're going to see these definitions and those words on your unit vocab test.
Yeah.
And
So hopefully that should be a little bit more straightforward with a lot less ambiguity.
again, at the same time, though, you need to do your job and study, memorize, and internalize these things, retain them. You might know them today, but will you know them tomorrow if you don't look at them again?
Seriously.
That is the
Most of these we
big
will use
question.
over and over again. We're going to start on page 3 and 4 in our packet, and let's get rolling.
Okay, take it away, Mr. Milks. What's a mole?
So first, a mole is the unit used to measure the number of particles or molecules.
Simple enough.
Simple enough.
M-O-L-E, M-O-L, versions. What's Avogadro's number? It is scientific notation, 6.02 times 10 to the power 23 particles or molecules. It is a mole.
That is the number in a mole.
Just like a dozen is 12, this is the number of particles or molecules in a mole.
Right. So we need to know it theoretically, right? We're not going to do too many calculations with it, though, right?
No, we don't do that. We skip the calculations. We just have to understand that atoms are tiny, and this helps us understand that.
Yeah. How many there actually is. So, gram formula mass, GFM. You will hear us refer to this as GFM pretty much exclusively, actually. We might say gram formula mass here or there, but we're going to say GFM a lot.
Yeah.
That is the mass of 1 mole of an element or compound in grams.
Avogadro's number is the number of atoms that we could never count, but since Avogadro's number and gram formula mass are related, we can count atoms by putting them on a scale and measuring them in grams.
Right, and what's nice is on your periodic table, it's going to end up being the atomic mass on the periodic table for
The
each element.
And you combine those when we make compounds, and you get the formula. Let's say. But we'll see that later. A mole coefficient. This is specifically to chemical equation notation, like how we write chemical equations. It is the number of moles of a reactant or product in a chemical equation. You'll see that as a big whole number in front of the formula for a chemical compound written in an equation.
Beautiful. Subscript, little tiny number at the end or within a compound. It's the number of atoms within the compound. The number refers to the element directly in front of the subscript. So CO2, we get that little 2, that means 2 oxygens, but only 1 carbon, because they're 2 different things.
Elements.
Two different elements. That's a great example, too, because we got to pay very careful attention that it's a capital C and a capital O is 2 different elements.
Not capital C, lowercase o,
which is
cobalt, and there would be 2 of the 1 element. Makes
Right.
the difference between
So
night and
yes,
day.
yes. Attention to detail.
Gotta know your notations, subscripts, coefficients, the element symbols. Gotta know it because this is the unit where it starts to matter because we're talking about equations.
Exclusively.
We're not talking about cobalt, we're talking about carbon and oxygen.
Right,
So,
and we start finding the mass of those things, your mass is going to be way off.
Right.
You're using a different element.
limiting reactant. This is a concept that's very simple to understand. Maybe more challenging to actually calculate in the lab. A limiting reactant is whatever gets used up first in a chemical reaction. It ends the reaction because there's no more
Of it left.
It would be like you're making peanut butter and jelly sandwiches and you run out of bread. Still got plenty of peanut butter, plenty of jelly, but you're limited in the number of sandwiches you can make because you only had 10 slices of bread.
Right. Now let's be honest. You try to substitute anything in there, you're not making peanut butter and jelly sandwiches anymore.
No, it might be a peanut butter and jelly wrap, or a different type of bread makes it a different type of sandwich. You know.
Right. But it's not the same reaction.
When you run out of ingredients in the kitchen, you don't make any more of what you were after.
Right.
or your recipe is going to be smaller than what you intend.
So we give it the name limiting reactant because it's going to limit how many you can make.
Bingo.
Beautiful. Law of conservation of mass. This states that matter cannot be created or destroyed, but simply rearranged. In our terms, our balanced chemical equations, whatever's on the left, it's got to be on the right.
Right. We're going to count atoms a lot.
Yes.
And we're going to rearrange atoms a lot.
Yep. Reactions.
And we need to make sure that none of them went missing because of this law. Right. It is beyond the power of man in the chemistry lab setting to create or destroy atoms.
Correct.
Okay.
Especially for our purposes.
Physicists can do this, and we'll study a little bit of it at the end of the year, but we can't force it to happen. We can only rearrange the things that we got.
And now, lucky you get combustion. You know you love this.
I love combustion milks, and I argue about whether it should be in this unit or not. The verdict was no, it shouldn't be, but it slipped in. So, haha, I got my way. This is a burning reaction, and any compound, when it burns, is called a combustion reaction. Oxygen is always going to be a reactant, meaning all burning things consume oxygen. The fire triangle.
Yep.
And all burning things produce carbon dioxide and water. So that's my little plug for combustion. I think it's snuck it way in somewhere else. Oops.
It's all right.
We'll move on.
It's fun. We all like to burn things.
Burning.
Balanced chemical equation is a representation of a reaction showing the reactants on the left and the products on the right, and it obeys the conservation of mass. If it's balanced, I have to have the same number of carbons on the left as I do on the right, same number of oxygens on the left as I do on the right.
Right. So these are the types of reaction that I like to put combustion into, but this is the basic, most generic form. Synthesis reaction. Synthesis itself means to create, and in our chemistry setting, we're going to combine two things into one thing. Now, these two things might be elements, these two things might be compounds, but the basic nature of a synthesis is you're taking multiple things and putting them together to make one.
Right, and that's why it says things. We don't want to limit it to elements or compounds, make it too ambiguous.
And we didn't want to give you the word species because that might confuse you with biology, but things.
But it does follow this format at the end, right?
A plus B makes AB. So if you were going to code up your elements in a compound, give a certain element A and a certain element B, you would see that this format plays back. You can apply your generic sequences to figure out if any chemical reaction is a synthesis, using these codes that we'll teach you how to do.
Good. And decomposition is actually the opposite. It decomposes to break down. So now this is a reaction that breaks one compound into two different things. So I got AB breaking apart into A and B.
And again, we'll teach you how to codify the reactions so the A's and B's make sense, because there's no element A, and there's there is an element B, but we're not talking about boron.
No, I mean, B could be carbonate.
Right. It could be lots of different things.
Right.
Codes. Code words. Yep. A single replacement reaction. This is a cool one where a single element by itself swaps into a compound, kicking somebody else out.
There you go.
So the generic format is compound AB reacts with the element C to make compound CB and element A.
Right.
Yeah.
We good?
Yep.
Double replacement, very similar, except for now I'm going to switch out two elements. So the reaction where two elements switch with one another,
right.
AB plus CD specifically goes to CB AD, because A and C got to be positive.
Yeah, the A and C are the metals, and the B and the D are the non-metals,
right.
The polyatomics. So it's like doubles partner switch.
Yep.
And you'll see more about that later.
Yep, double replacement.
So molecular and empirical formulas are an interesting part of this unit. Molecular formula is like the straight-up formula for the real molecule. Like H2O is H2O because we scientists, we figure out that the hydrogen and oxygen form in a 2-to-1 ratio. So the simplest way to represent a water molecule is saying H2O. That's a molecular
what it actually is.
And that's what it actually is.
Right. But
molecular formula. Sugar, C6H12O6, 6 carbons, 12 hydrogens, 6 oxygens. That is a straight-up molecule.
And exactly how it really exists.
Now, the empirical formula is when we look at the basic, most simplest ratio.
Right.
For H2O, it's 2-to-1, 2 hydrogens to 1 oxygen. That molecular formula is the empirical formula. For C6H12O6, you can reduce those subscripts to 1 to 2 to 1. So the empirical formula's simplest ratio with air would be C1H2O1.
Right.
And so it's about formulas and ratios. That's what all these things are about. And
they'll have a use for us.
Yeah.
They will have a use for us, but we definitely need to know their definitions.
Percent mass.
Pretty basic. It's the percent by mass of each element within the compound. So I can add up the mass of the whole compound and figure out what's the percentage of its oxygen, what percentage of it is nitrogen, that kind of thing.
And the purpose of doing this is in service of figuring out what the molecule's formula was.
Right.
So the empirical molecular percent mass, these are all kind of related.
Yeah, we're going to use them together a lot.
We need to know percent mass so that we can do the others.
Right.
Exactly.
Very good. Very good. Product, substance that is formed with it, the result of a chemical reaction. So the products are end piece.
Yeah, they're always on the right-hand side of our chemical
Yeah,
reaction
we do
arrow.
not want to get that wrong this year, right?
Never. Never.
Never. It's not really an option.
No, you can't afford to not know where products and reactants are in a chemical reaction.
I like to think that reactants react to form products.
To form, and the arrow means to form.
Right. So, and then the reactants now are
Substances that participate in the chemical reaction. These are the ingredients, okay? Everybody's cooked in the kitchen before. You call them ingredients. We, as chemists in the lab, call them reactants. That's just a code switch. Name, synonym.
Right.
It's all there is.
because the reactants are going to do what?
React.
They're going to react.
And produce
Products.
Yeah,
That's it.
there you go. So yeah.
Almost done.
Last little bit.
Polyatomic ion. This is specifically an ion made up of two or more atoms. The ion's the key word. They are usually covalently bonded, and we have a nice table in the reference table to let us
Reference table. Yeah, this is actually from previous unit, but we're going to see them a lot in this unit. They're not going away, people.
know. No, and when we have many of them, counting is going to. This is where it's going.
Right, because
could
this
get
is
a
where you
little
get
bit
the
crazy.
parentheses, counting atoms.
Yep.
You got to recognize that it's a polyatomic ion.
There you go.
A hydrate. Hydrates are certain class of substances that have water attached to the chemical formula. So the chemical formula can be by itself with water molecules attached to it. We're going to heat some of these things up in the lab and actually drive and evaporate the water off, and you'll see that a chemical change has in fact occurred.
And now we can calculate the percent water in the compound.
That had gone left, yeah.
Right.
Good one. Last bit.
Parentheses is a notation in a chemical formula that basically means the polyatomic ion sticks together in little packets. I could have two of them, I could have three of them, I have four of them, but I got to put a parentheses around that polyatomic before the subscript to show that that polyatomic stays together.
Right. It goes along with the polyatomic ion. It's a part of just chemical notation, recognizing that this formula has something in it that there's more multiples of them. It's
Right.
like groups. It's packets.
Yep.
It's a great way to call
Right,
it.
and mathematically it helps for us because it's what we already know. Distributive properties are going to
You're
work
gonna
the same way.
you're gonna distribute subscripts into the parentheses for a polyatomic ion, and it's
Just like
gonna
you would in
feel
math class.
just like mathematics, but it's gonna look a little different because it's chemistry.
But in
So
theory, it's the same thing.
it is the same idea.
Beautiful.
So know the vocab. You can't afford not to. Right? We had
No,
too
we're gonna
many
use-
too many students last unit didn't do their vocab quiz, and it hurt them because they didn't want to know their vocab.
Well, not even that, but listen, now you know it ahead of time. You took the notes, you did it, you know it, so you
Yeah.
should feel
It counts
a
as
lot
the
more
homework.
confident going in
Right.
to do it.
Counts as a homework grade. So,
Right.
All right. Thanks for listening and watching.
See you guys.